Okay, we're going to look at random variables now, and I'll start with this weighted question of what is the difference between fate and chance, and I don't really know. I guess people view fate as being something that's predetermined, something that's inevitable, and chance is something that could go either way in the future. That's closer to the idea of probability. Perhaps an important distinction now to make in mathematical terms, at least, is this distinction between uncertainty and risk. When we refer to risk, we're talking what are the odds? What is the chance of something? What is the probability of something? These terms are used interchangeably. Risk specifically means that we know in advance, or we have some kind of a subjective method to determine the probability. So like rolling a fair die, chance of winning a lottery, a card game in a casino. Uncertainty, on the other hand, is when the probability is subjective in the sense that we don't know, there's no clear way of estimating the chance of it. For example, what is the chance a person will walk on Mars before the year 2050? We have no way we can estimate or come up with some mechanism to decide what the chance of that is, but it's subjective. I want to make a little point here, is that, and this is not a small question because it's very closely related to the way that the modern physics is understood. You may know that there's two branches or two ways of viewing modern physics. One is relativity. It's the idea that you can't go faster than the speed of light, and time is adjustable. There's another area called quantum mechanics, which is involved with the idea that the precise position is whether a particle works as a particle or as a wave. And I'll give you a quick example of this, how this is related to chance or probability. Is that many people imagine that the atom looks something like this. This is a model that's used. You've got a little nucleus, you've got these electrons winging around. But this is actually somewhat false. The atom looks, because of quantum mechanics and because of the way quantum mechanics operates, this is closer to what an atom would look like. And you'll notice that these yellow and blue lines, spaces, refer to really a place where an electron could be, but it's not in any particular location at any time. And this is closely related to probability, and we'll come back later to this because I want to talk about the bell curve and the normal distribution, why it's so significant. In this course so far, but probably in the course in general, we'll be looking at something called a PDF, or a probability density function. And that's really just a method to assign chance to or probability to a random variable x. Now, we've seen a few of them. Take a quick glance at these. A binomial, for example, that would be a dichotomic variable. For example, somebody's left-handed or right-handed. And so we sometimes write it like this. X is a random variable. Until we meet a person, we don't know if they're left-handed or right-handed. Of course, there are people that are ambidextrous that write with both hands. But I'm just going to ignore this. Now, you notice that there's a parameter here, pi, which represents the chance of success. So in the case of left-handed, right-handed, we'd say that the chance of somebody being left-handed is around 11% or so. That's based on data that's been collected. Another PDF that we've seen we'll look at is that uniform. For example, this could be for continuous or discrete. One fair die, if you roll a die, you've got an equal chance of getting something. It could be a car breaking down in a tunnel, something like this. This is referred to as uniform. It's equally likely. Then, of course, we've seen also the normal curve, the bell curve. This is for heights or for R-score. This could be used for a discrete variable. Typically, it's continuous, and that's how we'll be looking at it. The normal equation itself, though, is actually continuous. And you'll notice here there takes two. Each PDF is a little bit different. This one takes two parameters. The one on the right is the spread. That's the population spread, or population sigma, and then this one here is the mean, the population mean. And to be able to determine the position of a normally distributed random variable, then you'd need to know both of those parameters. We've also seen the chi-squared, which in this case requires degrees of freedom to be able to look it up on the table and find out what the specific number is. Of course, there's many other PDFs. They're not limited to 4. Pick some random examples here. So a date of a person's birth. Until the person is born, you don't know what it's going to be. The number of siblings you may have. Again, you don't know. The date you might first marry. The amount of money you have in your bank account, or the amount of money you will have in your bank account in 20 years in the future. So, and these all would follow some kind of a probability density function. Sometimes known, sometimes not known. I want to talk now a little bit about the idea of an event and the probability of an event. So take this. This is how it was written in mathematics. We'd say event one, which is arbitrary, but E is the standard notation for this. The first child is a girl. So we could talk about the chance of this being true. Now, usually I say it's 50-50. I think actually it's in Canada, it's about 0.48, something like that, which is to say that all events by definition have to vary. Probability of an event occurs, has to be between 0 and 1. So as I said, we define it as a decimal 0.48, but 0.5 is okay. Now we have a second event, first child is a boy, for example. Now, we could write this again as PR. Here, I'll just do it here quickly. PRE2 is equal to, well, I don't know what it's equal to, but I think it's around 0.51. Slightly few more boys are born than girls. You'll notice something. These two events are mutually exclusive. That means to say if it's a child, if the first child's a girl, then it can't be a boy, and if it's a boy, it can't be a girl. And I'm doing this now by the definition by chromosomes. If this is the case, we have mutually exclusive events, and we can add the events together. So we could sort of say now that the probability of event 1 plus the probability of event 2 is equal to 1. It may not be equal to, one would expect so. Take another example. The event 3, let's say, it's a red card, a deck of 52 cards. You've got half are black, half are red. The card is a club. Well, these are mutually exclusive events. If you get a red card, you can't get a club. So in this case, since they're mutually exclusive, you can add them together, and we would say in this case the chance of getting either one or the other is going to be 0.75. So because they're mutually exclusive, you can add them together. But consider this possibility. Event 3, card is red, but event 5, a card is a diamond. Well, these are not mutually exclusive, so as a result, you can't add them together. And in fact, the chance of either of these events occurring would be 0.5, which would be the same as having event 3. Something we're going to be looking at in this course is the notion of conditional probability. And you'll notice I do it here by drawing a straight line between two events. So I've got event 1, the first child is a girl. The second child, event 6, is the second child is a girl. So this straight line means that we know that event 1 has occurred. So it's now a woman that, for example, has had a child. Her first child is a girl, and now she's thinking, she's pregnant, and she's thinking of she's going to have a second child. What is the chance that the second child is a girl? Well, we know that event 1 has occurred, so now we're looking at the chance of event 6, and let's put this in the context of cards. If we say event 3 is card is red, event 4 club, well, we know that event 4 has occurred. What is the chance the card is a red card? Well, we'd say the chance is 0. So this case here, incidentally, is 0.50. And we're going to get back to this idea. But for the moment, I just want to show this notation of this straight line. So we know that the event on the right hand has occurred. We're looking at the possibility of the second chance. So now we can get to the idea of independence. Independence means that if the probability of, for example, the second child is a girl is the same as if the probability without condition, then we can say these two events are independent. Take this example down below. We can't say that this is true because, if it's a red card, well, it can't be a diamond. Rather, it can be a diamond, but it's not the same chance. This means that we've provided, event 3 provides us useful information in making the prediction of it, whether it being a diamond or not. The chance of this happening all by itself is, chance that the card is a diamond is 25%. The chance of it being a diamond, knowing that the card is red, is 50%. So you'll note that none of these events are mutually exclusive. That you could have a first child as a girl and the second child as a girl. In the case of the red card and diamond card, they're not mutually. You can have those simultaneously as well. So the idea of mutually exclusive is very distinct from independence. Independence means you receive information; it doesn't help you to change or to make a prediction about the other event. Mutually exclusive means the two events can't occur simultaneously, or can't occur. One event precludes the other event. Now, I want to take a look at this, apply this idea a little bit, and we're going to carry on with doing this in a quiz. Consider a family of 3 children. So the first child, let's say, can be a boy or a girl, and we'll do 50-50. Now, These are mutually exclusive, and we're going to imagine each of the children that are born is independent. The sex of the first child is, the second child is independent of the first child. So, second kid, what can happen? Well, if you have a boy for the first child, you can have a boy for the second one. You could have a girl for the second one. Of course, if the girl is the first one, you could have a boy, and then you could have a girl. So we're looking at, these are the different possibilities. And each root here is equally likely because it's a 50-50 chance. And there's no likelihood of going one route or the other because, as we say, these are independent events. I mean, you say the sex of each child. Let's go to the third kid. Once again, we could take the root of a boy, and then could be a boy or a girl. Once again, we could take another root, boy, girl, and then third child would be either one, and so on and so forth. So we can sort of say now that each of these roots going down from boy down is just as likely as the other. And you'll notice here, if you count them at the bottom, there are 8 different paths that are possible. So what is the chance of having 3 boys? Well, you'd have to, in that case, go boy, and you'd have to be taking this route here. And it's the only one that would do it, so we can say that the chance of having 3 boys is 1 in 8. If, on the other hand, we said you have 2 girls, then 3 boys, well, I didn't say 2 girls, they're just a family of 2 girls and 3 boys. Well, one way to do it would be to go this route, and then this route. Another one would be to have a boy first, and then have a girl and a girl. And finally, you could mix them up. You could have the girl, the boy, and then the girl. So you could take this route. So there's this route here, and this one here, which means that there's 3 chances in 8. So it's about 37.5%. What we're going to do in this next quiz is to extend this idea out to not 3 children, but 10 children. And furthermore, we're going to do it with a village. Imagine a village of 1,000 families. Each family has 10 children. And to do this on PowerPoint would be really take up a lot of space, take up a lot of time. So we're going to be doing it with the computer instead. And we'll be doing it with something called a Monte Carlo experiment. If you know, Monte Carlo is in southern France. It's in Monaco. It's famous for having a casino. And so this is sometimes referred to as a Monte Carlo experiment. So it's like conducting a casino experiment with the computer instead of actually going to the casino and losing money.